Hello everyone, I hope you guys are doing great. In this video, we are going to learn about the MPC Type Beam in Abaqus. This video is related to my latest blog post that is about it. And in here, I have taught about this type of constraint using 4 examples. So here I have my first example, this model. And this is a very simple model that uses the MPC type constraint. And the idea of this model is to intuitively or visually see how this type of constraint works, because I guess this is the best way to understand about this type of constraint. So in this video, I'm going to build the models used in this blog post. That is, we are going to build this model in Abaqus. And so this is the first example. And then here we have the second example. The difference is that we are going to use kinematic couplings here. And then the third example is this one. There is a subtle variation that we are going to see shortly. And then there is the fourth example, this one. And also here I'm going to show you a real application of this type of constraint. Okay, so this is actually a structure that we have modeled for one of our clients. And the idea here was just to evaluate the stiffness of this structure. I'm going to talk about it at the end of this video. Okay, so basically here in this model, we have the application of MPC Type Beam. Before we start working on Abaqus, let's just define what is an MPC Type Beam. So MPC Type Beam provides a rigid beam between two nodes to constrain the displacement and rotation at the first node to the displacement and rotation at the second node. So this is the definition provided by the Abaqus Analysis Users Guide. Actually, this is not the name. It is the Abaqus Analysis Users Manual. I have let the link to this manual, where we have here a topic about general multi-point constraints. So MPC means multi-point constraints. Okay, so basically the MPC is a rigid beam, that is a beam with infinite stiffness. That's basically that. And one useful application of this type of constraint is to simplify bolted connections. So when there is a bolted connection in some part of the model, and we are not interested in analyzing the regions near to this connection, that is, we are not interested in analyzing stress, for example, near to this region, then we can simplify this connection using this technique that I'm going to show you in this model. Okay. Okay, so let's start building this model right here. First thing I want to do is to create our working folder. So go to any part of your computer and then create a new folder. Let's name it as MPC example. And then open it, click here, and then get the path, that is Ctrl+C, copy it. And then let's open up Abaqus CAE application. And then click with standard explicit model, and then go to File, Set Work Directory, and then paste that path here. And for now on, everything that is generated from this Abaqus session is going to be saved in that working folder. Now, the first thing we need to do is to create this part, this lug. This is going to be a shell. This is going to be represented as a shell element with a thickness of 3.2 mm associated. To create this part, we can go to part module and then click on create part, name it as lug. This should be 3D, deformable, and shell. Continue. And now get the circle tool, position the mouse in the middle, right in the center actually, click, and then the second point to define the circle, you should click here where I am clicking on the right side. This point is important. The second point that you use to create a circle is important because you're going to force the software to create a node here later when we get to generate the mesh. Okay, now create another circle and then position the mouse here, for example. This second point should be aligned with this one, because then we are going to have a node here and another node here, and then the mesh is going to be better looking here. Now get the rectangle tool, position the mouse right in the bottom region here, click, and then position the mouse here in a way that we are going to have the height of this rectangle exactly equal the height of this circle. Now let's get the trim, auto trim tool, select this one, and let's get hidden of the lines that we don't need. You should just click on the lines that you don't need, and then it's going to be deleted. Now click on Add Constraint tool, select Tangent, and then select this line, then this line. Now you see that we have the symbol here showing that these should be tangent, and this line and this line. Okay, now let's get the Add Dimension tool and then click on this circle. Could be 15 mm. Click on OK. Click on this one. Could be 23, I guess. 23 is better, or even more. So click on Edit Dimension. Click on this one, and maybe 24. Yep, that 24 is better. And then click on Add Dimension again. Select this line, and let's increase it to maybe 90. Okay. And then click on Ask and click on Zone here. And there we have it. Now, next thing I want to do is to partition this surface in order to create a better looking mesh. Okay, so you see that in here, oh, it's not so easy to see it here. So, but we have a circle here in which we have nodes. So let's do this. To do the partition, select this tool, create partition. And then I want to create this partition on a face. And then the method should be sketch. And then it says select an edge or axis that will appear. We can select any edge. And then the first partition I want to create is a circle around here. So select the circle tool. First point should be the center. And then second point should be around here in the bottom region. And then this second point is important too, because we are going to have a node here. So it's important to be aligned with this one and this one. And then click on Add Dimension. Select this circle and then define it as 19 mm. Okay. Or even we can increase it a little. Edit dimension value, select this one in 19.5. Yep. Okay, 19.5 is better. Another partition I want to create is select the line tool and then click right in the middle on the top part, and then also here right in the middle, and then middle mouse button to conclude the operation, and then create another line like this. Middle mouse button. Okay. And now press Ask and then click on Done. And you see that this part is splitted in some regions, but it doesn't mean that it's not connected. This is a single part, but these divisions is just to make some divisions in the mesh itself. It's not real physical divisions in the part. Okay, that means that this mesh is going to be continuous throughout these boundaries that we have created. Okay, now the next thing I want to do is to create a mesh for this part. Let me close this window, and then you see that here we have this parts item, maximize it, and then we have our part lug, maximize it, and then we have this item mesh, which is empty. Double click on it, and then now we have switched to mesh module, and then we have our part here selected. First thing I want to do is to seed this part, so click here on seed part. This tool is used to define the mesh element size. So I want to use 5 mm size for the elements. Click on apply, and you see that these points are generated on the edges, showing the element size. Click on OK. Next thing is to click on Assign Mesh Controls, select everything, middle mouse button, and then select Tree. I want to have triangles here, and then click on OK. Next thing is to assign element type. So select, click on Assign Element Type, select everything, middle mouse button. And then I want to use second order elements. So click on quadratic, because since we're going to use triangles, first order triangles are not, the accuracy of this type of element is not good. It is called a constant strain triangle. And for triangles, we should always use quadratic order. And then we are going to have the mid-side nodes. The interpolation function used for the displacements are going to be second order. And anyways, it's a better element. Click on OK. And then after that, we can ask the software to mesh this part. And to do that, we can click on Mesh Part and then say yes. And now you see that we have a very good looking mesh. Okay. All right. Next thing is to create a material. To do that, double click on material and then name it as steel. We are going to create a standard linear steel. The material is not going to be important for us here in this analysis, because we just want to see how the MPC behaves. For this material, assign a mechanical elasticity, elastic property. And then now we should define the set of units we are going to use. So if you go to Google and then search for Abaqus units, and then let's go to images, and then we have these. We should select one of these set of units. And in this case, I'm going to select this one as IMM. So length should be in millimeters, force in newtons, mass in tons, time in seconds, stress in MPa. Okay, so if stress is in MPa, the Young's modulus should be in MPa too. So for a standard steel, the Young's modulus is usually equal to 200 gigapascal. And here we should put it in megapascal, so it should be 200,000 megapascal. Okay, 5 zeros. And then Poisson's ratio is usually equal to 0.3. These are the only mechanical properties that we should have defined for the material for this type of analysis. With these two material properties, we can define the element stiffness. Click on OK. And now we have our material created. Still, next thing is to create a section. So double click here on sections and then name it as lug underline section. And then these should be shell and homogeneous. Homogeneous means that the mechanical properties doesn't vary with position. That is, the Young's modulus or Partition's ratio in this point right here is the same as in this point right here, or in any point in the lug. Continue. And then here, we should define a shell thickness. And as I mentioned before, this is going to be 3.2 mm. That is an 1/8 of an inch. And then the material should be steel that we have just defined. And then click on OK. And now we have our section. And next step is to assign this section to this part. To do this, click on Assign Section, deactivate Create Set. There is no need to create any set. And then select everything, middle mouse button, and then select the section we have just created. And then the definition of the shell offset should be middle surface. And then click on OK. To rotate this part, hold the Ctrl, Alt, and then use the left mouse button like this. And when we let middle surface for the shell offset, it means that for the 3.2 mm, half of it is going to be offset upwards and the other half downwards. Okay, now we have the section assigned. That means that now the software knows what should be the material used for this part, and it also knows the shell thickness and everything. Next thing is to create an assembly with two identical parts positioned like this. So let's do this. To do this, go to Assembly, maximize it, and then we have this item instance. So we are going to create an instance for this that is one assembly. Double click on it, and then we have only one part available for this instance, and then select this part and then click on OK. Now I want to have one more of this part. To do that, you see that now we are on the assembly module, and then we have this tool, create instance again. And then you should select this part again, but now activate the auto offset from other instances. Click on OK. And now we have the two instances in our assembly. First thing is, I want to rotate one of these instances by 180 degrees. So click on Rotate Instance, and then click on this one, middle mouse button, and then click on the Z axis here to be the rotation center and direction. And then let's define the angle of rotation to be 180 degrees. Click on OK, and then click on OK. Now let's use the Translate Instance tool, this one, middle mouse button, and then from this point that is right in the center of the circle to this point. Middle mouse button, and press ESC, and I want to translate this instance 15 mm upwards. To do that, firstly, I need to create a reference point that is 15 mm upwards from this central point. To do that, click on Create Datum Point and hold it until you see these options. And then select Create Datum Point, Offset from Point. Select this one, and then I want to offset it upwards. So you see that we have here the X, Y, and Z components. And I want the Z component, because you see that we have the coordinate system here and Z is upwards. And I want the Z component to be 15, then press enter. And now we have this new point that was offsetted from this one by 15 mm in the Z direction. Now use the translate instance tool, activate it, select this instance, middle mouse, and then select this point, and then this one as the second point, middle mouse button. And now we have it positioned. I guess I'm going to move it a little more upwards. Yeah, it's too near, maybe 20 mm is better. So let's do this. So click here and then click on this point, and then here define it as 5 mm, press enter. And now you see that we have this point here, this offsetted by 5 mm upwards. Translate instance, this one, middle mouse button, select this point and this one, and then middle mouse button. Okay, now it's looking better. I want the parts to be far from each other because I want to see the MPC working in a way that helps you to understand how this type of constraint works. Okay. All right. Now the next thing I want to do is to create the couplings. This blog post or this example here is not, we are not going to focus on the coupling constraints, but we should use it in this case. However, if you want to see something that is completely focused on coupling constraints, we have a blog post that is about it. I'm going to let the link in the video description. This is the blog post. And in here, I talk about everything related to kinematic and distributing coupling constraints. Okay. And also, I have mentioned before that this type of technique is used to simplify bolted connections. However, when we want to analyze the bolted connection itself or regions around it, we should represent the bolted connection using bolts, the bolt, nut, and washer, and define the contact between the parts. And also apply the bolt pretension. And there is also a blog post that I talk about techniques for bolt pretension in Abaqus. This one. Okay, so here I talk about two different techniques that can be applied for bolt pretension. I'm going to let the link to this blog post in the video description too. Okay, so let's go back to create the couplings. So our first example is considering two distributing coupling constraints and one MPC connecting these two coupling constraints. Okay, so this is the first example. Let's do it. Go to module, select interaction, and then to create the coupling, firstly we should create a reference point. So click on create reference point, and then click on this point right here, right in the middle. And now we have RP1, and then also create a reference point here. And then we have RP2. Now click on create constraint, and then select coupling, and then continue. And then it says select the constraint control point, select this one, RP1, middle mouse button, and then select the constraint region type, select node region, and then select this surface hold the Shift button and then select this surface, this one, and this one. Okay, so to select multiple entities, you should hold the Shift button. And then now we have 4 surfaces selected, middle mouse button, and then here we should define the type of coupling. For this first example, we should select continuum distributing. So continuum distributing is a type of coupling that is deformable. It is not completely rigid. And the kinematic coupling is completely rigid. So let's start with the deformable one. Okay, and now we have the coupling created. Let's do the same thing here. Create constraint coupling, select this middle mouse button, and then node region, select these 4 surfaces, middle mouse button, continuum distributing, and then continue. Now, the next thing is to create the MPC Type Beam constraint. And this MPC is going to be created using RP1 and RP2. That is the reference node of the upper coupling and the bottom coupling. Okay, and we are going to use, let me go to these, and you see that the green node here is going to be our MPC control point, and the this bottom node is going to be our MPC slave node, that in this case is a single node. Okay, so the MPC control point is the first node that we select, and the other nodes are the slave nodes. Let's do it. To create it, go to create constraint, and then we have MPC constraint. Click on continue, and then it says select the MPC control point. It's going to be this upper node, RP1, and then select regions for these slave nodes. In our case, we are going to select a single node, but we are going to see shortly that we can select regions like surfaces and things like that. Middle mouse button, and then here we should, you see that this window pops up, and then we have the name of the constraint, the type, that is MPC constraint, the control point, which was picked, the RP1, slave node, which is RP2, and then MPC type. You see that we have all these types, and the one that we are going to focus on here in this video is going to be the beam MPC type. Okay, which is the most used one for structural analysis. And then click on OK. And now we have the MPC created. You see that it's written beam, MPC beam. It's not so easy to see, but it's written something like that. Okay. Okay, now we have our parts connected to each other by using 2 distributing couplings and 1 MPC connecting the couplings. Okay, and this is representing a bolted connection. So if we wanted to represent it in a more realistic manner, we should have a bolt, a nut, a washer, contact defined between the parts, and then apply bolt pretension. Okay, now the next thing I want to do is to create a step. So you see that here in steps, we have just the initial step. We can use the initial step just to prevent rigid body motion. That is just to apply some boundary conditions to fix some specific part. And we should create another step to apply loads. So let's do this. To create another step, double click on steps, and then the create step window pops up, and then we can name it as load step, and then it's going to be static general. So we are going to run a static structural analysis here. Continue. And then we should activate the non-linearities due to large displacements, because in this case, since we're going to apply large displacement to cause a large deformation, we are going to have the effect of large deformation. So we should have this activated, and then click on OK. And now we have our new step created. So the first boundary condition that I want to apply is this orange one. I want to fix displacements and rotations of this edge. And I can do this in the initial step. So you see that we have this item here, BCs, that is boundary conditions. Double click on this one. And then the type of boundary condition, we can name it as fixed left edge. And then this is going to be a symmetry encastre boundary condition. Select this edge, hold the shift button and select this one, middle mouse button. And then I want to encastre, that is, I want to set all degrees of freedom, that is the translationals, U1, U2, U3, and rotationals, UR1, UR2, and UR3, equals 0. So let me activate the mesh, click on show native mesh, and you see we have all these nodes that are part of this edge. So we have 1, 2, 3, 4, and so on. And for each node, since these are shell elements, we have translational and rotational degrees of freedom. And then basically we are saying to the software that these should be all equal to 0. Okay, so here we are going to have this edge fixed in place. Now, this other edge, I want to displace it in the positive X direction. You see here the coordinate system. I want to displace it in the positive X direction by 15 mm. So it's a large displacement. It's going to deform the parts considerably. But I want to apply the displacement on the load step that we created. We can't apply non-zero displacements in the initial step. Okay, so let's do this. Here we have, in this step, click on it, right click on it, and then say make current. Now go to load module, and then we have this tool, create boundary condition. And this is going to be named as disp 5 mm X. And then this is going to be displacement. Click on continue. And then the displacement is going to be in the X direction. That is U1. U1 is X, U2 is Y, and U3 is Z. And this is going to be 15 mm. Click on OK. Oh, I didn't select the edge. So to fix that, you see that it has applied this displacement to this edge here, which is not where I want. So to change it, click on Boundary Condition Manager. And then you see that we have this boundary condition fixed edge, left edge created in the initial step, and it was propagated to this load step. And then this one is the boundary condition that we want to edit. Click on edit. And then you see the region is picked. I want to edit region. Click on this. And then click in any region of the screen to deselect that edge. And now select this one, shift, and this one. Middle mouse button, and then click on OK. And there we have it. Okay. I guess we have everything set up. We can create the job and solve this model. To do that, go to job and then create job. It could be job 1, that's okay, continue. Or actually, let's create it as first example. Click on continue, and then click on OK. Go to job manager, and then you see that we have our job created, and then click on submit. Since we have defined our working folder to be this folder, as I mentioned before, everything that is generated from this analysis is going to be saved in this folder. So you see that, let's go to monitor. So since this is a nonlinear analysis due to large displacements, this software needs to solve it interactively. That is, it can't apply the 15 mm displacement completely. It started applying 25% of it, and then another 25%, and then it needed to decrease to 6% until it reached 100% of the 15 mm. So dismiss, the model has been solved, and then go to results, rotate, and then here we can plot contours, and then here we have the parts deformed as we expected. So here I have also this image. So you see that in this image, we can see the coupling and we can see the line representing the MPC. Here in Abaqus visualization, for some reason, I cannot see it. I also tried to go to view, ODB display options, and here I have these constraints, and you see that show multi-point constraints is activated. Distributing couplings is activated, and show kinematic couplings is also activated. So it's not showing. And there is one thing that we can do, that is go to display groups and then double click on it. And then here we have distributing couplings. You see that we have these two, select these two, and then click on add. And now we have the coupling represented here. Now to represent the MPC, we have this one, MPCs, but you see that it's not appearing here as an option. So I don't know if it's some bug in my Abaqus, but if you see some option here, in your case, you should just select it and say add. In my case, it's not showing anything, so I'm not being able to see the MPC. And there is one software that I use for post-processing. It's not related to Abaqus. And in this software, I'm going to show you guys this model shortly that uses MPCs. But here I can get that analysis results and plot it here for us to see the MPC. So let me do this. This part, you should just look at it. I guess you will not have this software installed. The idea is not to show how to use this software here. Let me go to this working folder where I have the files of this model. And then you see here I have the .inp. This file has all the information related to this model setup. Let's open it. And then here I have the model. So you see that we have the coupling. Let's show the mesh. We have the couplings and we have the MPC represented by this red line. And then I'm going to also insert here the results that was generated. The results are all saved in this file, the .odb file. Okay, so here I have it already uploaded. And then I'm going to get von Mises stress, read, and let's plot it. So you see that now we can see the MPC deforming. Okay, so the idea of this example is to show in a visual way how this type of constraint works. You see that this is a rigid beam, that is, it doesn't deform, which means that the distance between these two nodes is kept constant. This upper node is rotated if the beam is rotated. So you see, look how this node right here is rotated in the counterclockwise direction, because we have the MPC rotating. And also this bottom node is rotated in the counterclockwise direction because of the MPC. And when this node is rotated, since we have this node attached to a distributing coupling that is attached to these nodes, then for that reason we are also rotating this surface where we have the coupling defined. Okay, and so this is what happens. You see that the stress here is like 35,000 MPa, which is really high, and it's well above any type of steel yield strength. The idea here is not to analyze the stress and to see if the part is going to fail. I just want to show you how the MPC works, okay? All right, now let's do the other examples, and it's going to be fast. We just need to do some quick adjustments. So go to interaction module, and then click on Constraint Manager. We have these two couplings, you see? Now go to coupling 1, edit, and now I'm going to use Kinematic. Select Kinematic, click on OK. Now this coupling is going to be rigid. Do the same thing for coupling 2, Kinematic, click on OK. The constraint 3 is our MPC beam. Okay, now go to Job module, close this, and then say create job, and then this is going to be second example. Click on continue, click on OK, job manager, and then select the second example job and submit. Now let's wait it, solve the model. It's going to be solved very quickly. And while it's not solved yet, let me show you this example. Actually, I guess let's see. Yeah, it's completed already. Let's look at that example later. Okay. Now let's go to Job Manager. You see that this is completed. You can click on Results. Let's see how this looks here. And then click on Plot Deformed Shape, and you see how this deforms now. Click on Plot Contours on Deformed Shape, and then here we have the vomice stress plotted. And you see that now the surface where we have used to define the coupling, since this is a kinematic coupling, now this surface is rigid. So that means that it doesn't deform. You see that it's kept. It doesn't deform. It just rotates as a rigid body. And the same thing happens to this surface. Okay, I can also put this model here. Let me do this. So it's second example. New window, results, reads, show mesh, and let's plot results. And then you can see the difference. You can see the difference. You see that this surface here where the coupling is defined, this is for the distributing coupling. For first example, you see that this surface deforms, right? Now, in this case, look at how this surface is straight. It didn't deform, it just rotated as a rigid body together with the beam MPC. Okay, so in this case, you see that at the beginning of the analysis, the direction of the beam MPC was normal to the plane defined by this coupling. Okay, which means that we have a 90-degree here between these two. And then after we have deformed it, the 90-degree, here we have 90 degrees yet. Okay, the direction of the MPC is yet normal to the surface where we have the coupling. Okay, and this is because everything here is rigid and then nothing can change. Like the angle here cannot change because if it changed, that means that it had deformed, and then we would have a stiffness associated to that. Okay, let's go to the third example. The third example. So for this third example, we are going to delete the coupling here in the bottom. And instead of using a coupling with only one slave node, actually an MPC with only one slave node, we are going to use multiple slave nodes. Okay, so let's do this. Go to interaction and then go to constraint manager. And then we have the MPC here. This second coupling 2, I want to delete it. So select it and say delete. Yes. And the MPC, that is constraint 3, in my case, I want to edit. So click on edit. And you see slave nodes, we have only this node selected. I want to edit region. Click in any region of the module to deselect that node. And I want to select this surface, hold the shift button, select this surface too. Oh, select this one. Do not select the edges. This one and this one. Middle mouse button, and then click on OK. And now there we have it. So instead of having the coupling here, we are going to connect the MPC using the control point here on this coupling. And these slave nodes are going to be the nodes that are part of these 4 segments of surface that we have selected. Okay, go to job and then click on create job. And then this is going to be third example. Continue. Okay, job manager, and then submit the third example job. Okay, so what do you think is going to happen? Before we had this situation, 2 kinematic couplings, in the second example, I mean, and then 1 MPC connecting like this. Everything was rigid. Now for this one, we have everything rigid yet. Go to results and plot it. And you see that the behavior is exactly the same as in the second example. We have yet everything rigid in this model. Let me put it here also. So let me go to third example in the results, integration point, read, plot, show mesh, and you see the representation. So everything that is red is MPC. So basically it's like we have many rigid beams. Each one of these lines that you're seeing here, the red lines, Each one of these lines is representing one rigid beam. So it's like we have several rigid beams here connecting from this node to each one of these nodes that are part of this surface where we had the coupling before. Okay, so this is what happens. You see that the maximum von Mises stress is 46,000 MPa, and on the last example, let me show it here. The last example I end up not having the I end up losing the results here. But in the last example, the von Mises stress was exactly the same. Okay, you can compare the results. I can get it here. Let me show it here. So click on plot contours on deformed shape, and then here let's go to results options, or not actually here. Let me just try to remember. Common labels. I don't actually use the visualization module in Abaqus to post-process results, so I'm not really sure. I don't remember where I should go to modify it. Well, that's okay. So you see that the maximum von Mises stress here is 6.1 E plus 4. And then for the third example, the maximum von Mises stress is exactly the same, 6.1 E plus 4. That means that these two ways of modeling these bolted connections using rigids is yields to exactly the same results. But in this case, we are eliminating one of the couplings, so this is more efficient. But it doesn't look so good for me because it doesn't resemble a bolted connection. Okay, but if you don't care about it, then it's okay. Okay, let's go to the fourth example. Go to interaction module. And then in the fourth example, which is this one, we are going to delete all couplings, and we are going to only use the MPC type beam with multiple slave nodes. So go to constraint manager and then delete this coupling, delete this one, and then let's edit the MPC beam. And the control point, we can keep the control point here. And the slave nodes, we can click on edit region. And now I should add this surface, hold the shift button and add this surface, this one, and this one, middle mouse button, and look, okay. For some reason, it has lost the selection of the bottom surfaces. So let's click on edit again, slave nodes, edit region, hold the shift button, and then select these surfaces. And also these ones, I guess, just click on it just to be sure that we have it selected. Let's see if it worked. Yeah. Okay, this is not looking exactly equal what we have seen here, right? Because I have put the MPC control point as one of the nodes that are in this surface. We can do this too. So to do this, so if we keep it like this, it's going to work properly. It's okay. But just to make it exactly equal this one, let's go to edit and then the control point, edit region, and then you can select any node here, for example, this one. Click on OK. See, there we have it. So let's go to job, create job, This is the fourth example. Continue. Okay. Job manager. And then submit the fourth example. But I guess you already imagine how this is going to behave. This is going to behave exactly the same way as this one, because we have yet everything rigid in this region. So it doesn't mean if we use two kinematic couplings and one MPC, or only one kinematic coupling and one MPC with multiple slave nodes, or if we only use one MPC with multiple slave nodes. Okay, but if you want to be efficient, you can only use one MPC with several slave nodes, which is what we have done here. So here we have the results for the fourth example. And then if we plot the von Mises stress, you see that the maximum von Mises stress is exactly the same as in the second and third examples, 6.1 E+4, which shows that it yields exactly to the same result. Okay. Okay, but let me point out one thing. If you want to use a distributing coupling and keep this surface deformable, and I prefer to do that because it keeps things more realistic, because it doesn't, you know, stiffen the part where in these regions here. Well, I guess it's better. It's more conservative. Then you should create two distributing couplings just like this and one MPC, just like we have it here. Now, before we finish this video, let me show you a real application of MPC Type Beam constraint. So here we have this analysis of this structure, where our purpose was to evaluate the stiffness of this whole structure when there is a force applied here in this region, highlighted by the red arrow. Okay, so this is a rotary kiln alignment system. Let me show you what is a rotary kiln. So a rotary kiln looks like this. And let me get this picture. So this whole thing rotates, and there must be a structure that prevents these to move in the axial direction. Okay, I'm not seeing anything like this here. Let me try to find alignment system. Let me see if I can find something similar to that. Yeah, this is an alignment system, but it looks pretty different than the one that we have there. So it's like a roller that is in contact with something in the rotary kiln that is fixed in the rotary kiln. So this prevents the rotary kiln to move in the horizontal direction or the axial direction. Okay. All right, so here we have that structure, and the purpose of this analysis was to evaluate the stiffness of the structure when we have a force applied in this region. Where would be the region where the rotary kiln would contact this structure? Okay, the surface of the rotary kiln is represented by this. Let me show here. By this. This is a rigid element, and basically what we do is, so there is an initial distance here, and then I'm going to displace this rigid element until we have contact, as you can see, and then I'm going to continue displacing it to deform the structure. Okay, and then I have applied a displacement to this element, and then I can plot force versus displacement, which is this curve right here. And then we have the stiffness evaluation. Okay, so this is how you evaluate the stiffness of a structure. Okay, so let's see how this looks like. So you see that the whole structure is deforming, while this plate here is fixed. Okay, so this is the boundary condition that I have applied here. I forgot to mention. Okay, so this was the purpose of this analysis. And since we were not interested in analyzing the stress throughout the whole structure or anything like that, I could simplify the bolted connections that we have throughout the whole model. Let me show here MPC and couplings. And you see that here we have many bolted connections, for example, between this plate and this other plate. Okay, these are shell elements. I don't have the thickness represented here. But you see that we have a distributing coupling here and another there, and then one MPC connecting the reference nodes, just like we did, just like we have done here. Okay, in this case, I need to have two couplings and one MPC because I'm using a distributing coupling. Okay, so you see that we have many bolted connections here, and the result, the evaluation of the stiffness, which was the purpose of this analysis, would not be affected due to this simplification. Okay, but if we were interested in analyzing stress in this region, then we would have to represent the bolt, nuts and washer and contacts and everything. Okay. Okay, I guess I'm finished. I know that this was a long video, but the idea here was to make you understand everything about MPC Type Constraint, MPC Type Beam actually, and this real application. So this is used in many modules. I use it in many modules. I work with front suspension of heavy vehicles, and in these models sometimes I need to consider the whole vehicle assembly, but the region of interest is just the front suspension. So for the rest of the vehicle, I should use some simplifications, and one of the simplifications that I use is this technique for bolted connections. Okay, well, I hope you guys liked it, and see you in the next video.